Oh, okay. Good to see you all. I'm glad it's Thursday again. It's one day to go. Okay, I'll try to make it quick, okay? Or I will try to make it feel like it's quick, so not to bore you too much. All right, we're actually getting to more and more interesting stuff. You can probably tell. Last time, at the end of the lecture, I talked about general curves in space. And I took as prototype the simplest curves, that is lines, right? And lines we found convenient to represent in parametric form, which means that we write each coordinate as a function of an auxiliary variable, which we usually call t, but not necessarily t. It could be any other letter of your choice. By default, we call t. And then each of the three variables is written as a function of this t. I'm hearing more people today than I'm used to. You spoiled me in the previous lectures. You've been so quiet, so let's keep it this way. So these are arbitrary functions in t a priori. And in the book, you can look at various examples. There are some pretty cool curves that you can parameterize this way. For example, a spiral, which goes like this, and many other ones. I'm not going to go over these examples because they're fairly easy to just read about in the book. What I want to emphasize is the fact that this is a natural generalization of the formulas we had for lines, for which these functions had very special form. They were linear functions. Functions of degree 1 in the variable t. I can wait. I mean, just knock them. Yeah, thanks. So that's what we have. Now I want to look at it in a slightly different way, and I want to think of this as not just a way to parameterize a curve, but as a function with values in vectors. Because the point is that when you have three coordinates, when you have x, y, z in general, you can view them as coordinates of a point in space, right? X, y, z. But you can also draw a vector from origin to this point. That's called the position vector of this point. So there's always this two ways of thinking about the triple of numbers x, y, z. This is a point, and this, which we also write as xi plus yj plus zk, is the position vector. And even though we realize that these are two different objects, we use essentially the same information to represent these objects. And so oftentimes it's convenient to interpret a triple of numbers in two different ways, as a point or as a vector. So if we interpret it as a point, we just think of this point as traversing this curve in free space. At each moment t, which actually you can think of as time, if you wish, it will be in a certain position. And as time goes by, it will trace this curve. But you can also view these three functions as components of a vector. So we get a vector value function, which we can denote as r of t. So that's a vector in which the first component will be f of t, the second component will be g of t, and the third component will be h of t. In other words, if this point lies on this curve, you can think of this point p moving along the curve, and so that its three coordinates are changing as functions of t, f, g, and h. But you can also think of the vector itself moving so that the endpoint goes along this curve. And that's what this function r of t represents. We're more used to thinking of vectors as static objects. We would usually talk about a vector, so it's a particular vector. But nothing prevents us from allowing the vector to change with time, say, or with some variable t. And then what we get is not a single vector, but we get a vector for each value of t. Each value of t gives rise to a particular vector, which we simply denote as r of t. So the convenience of this is that if we think about it in this way, we can use various operations on vectors and apply them to this vector value functions. For example, we can add two vector value functions. If we have r1 of t and r2 of t, we can take the sum. So that would just mean taking the sum of the components. So for example, you'll have f1 of t plus f2 of t, and the same for g and h. I just want to save time. I'm not going to write it in detail. You get the idea. If you were thinking in terms of points, you wouldn't be able to do that. It wouldn't make sense because we cannot add up points. We cannot add one point to another. But we can add vectors. We can use parallelogram rule or triangle rule, whatever you like. There's a rule for adding vectors. Vectors can be added up. So that's why when we convert this into a vector value function, we can use this operation, and sometimes it's very convenient. What is perhaps even more important is that we can approach this as functions and apply other operations which we normally apply to functions which are valued in numbers, like differentiation and integration. This kind of functions can be differentiated and integrated just like normal functions. And what it means is simply applying this operation to each of the three components. So it's very straightforward. You don't really have to think about it too much. You just differentiate the first one, differentiate the second one, and you differentiate the third one. And this is something which actually has important applications, because the derivative of this function will give you information about tangent lines and tangent vectors to your curve. So the derivative, that would be r prime of t. We use the same notation as for normal functions, but I shouldn't forget this side, which emphasizes that it is a vector. So that would be just taking the first derivative of f, the first derivative of g, and the first derivative of h. And so this derivative has a meaning, namely, if we take, I want to emphasize that I want to evaluate at a particular point, which I'll call t0. There's always this issue with notation. When I write something like r of t, there's a question, what do I mean by this? Do I mean a particular value for a particular t, or do I mean all of these values for all values of t as a function of t? And usually it's clear from the context. But now I want to re-emphasize that I take a specific value. That's why I call it t0. So this will not be viewed, I don't want to view this now as a function. I want to view this as a value of that function, the derivative, at this particular value t0. For example, t0 could be equal to 0, like in the example which I calculated at the very end of last lecture. So that would mean that we are evaluating the derivative at the point t0. So if we do that, this is a specific vector. This is a specific vector corresponding to the value of t, which I call t0, which is a specific value, particular number, some numeric value. And the upshot of all this is that this is a tangent vector. Tangent vector to the curve described by these equations at the specific point, which I'll call, say, x0, y0, and z0, which is f of t0, g of t0. And last time, at the very end of the last lecture, we looked at an example of this, how this works. At the very end of the last lecture. So once you pick a value t0, you have a particular point on your curve. Let me go back to this picture. So let's say this is the point P. So that would be the point x0, y0, and z0. That's the point which corresponds to the value of t equal t0. And then for other values, it's somewhere along this red curve. So if you want to calculate the tangent vector to this curve at this point, that's going to look something like this. So this is precisely this r prime of t0. Why does the derivative give you a tangent vector? Well, that's clear, because that should be clear from what we discussed before. Because what is the derivative? The derivative, by definition, is obtained as follows. We take the value, so the derivative at t0 is the value at t0 plus some small number. Let's call it h, minus r at t0 divided by h. So let's say this is the point when t is equal to t0. And let's say this is the point on the curve. That's the same red curve, so maybe I should use the same color. And there's a point equal to t0, our original point, which I call P on that picture. And this is the point P prime, which corresponds to some value t0 plus h. But remember, we also have the origin somewhere, so we have a coordinate system. I'm magnifying. I blow up a small part of this picture. But so there's a coordinate system somewhere in the background, and there's the origin, the point O, right? So r of t0 plus h is going to be this vector. And r of t0 is going to be this vector, the vector I have already drawn on this picture, this one. So, and I'm using the standard formula for the derivative. The derivative is the increment divided by the change in the parameter. The increment in the values, when you change the parameter by h, divided by the parameter. So it's like velocity. You calculate velocity by taking the difference between positions and dividing by the time, right? So it's the same idea. It's the same formula as for normal functions. We apply exactly the same formula for vector functions. So what do we get as a result? We have to subtract this vector from this vector, and we know how to do this by triangle rule. It's just the vector connecting the two. You see? So the point is that the difference between these two vectors is just the vector connecting them. You see, because why is it the difference? Because if you take this plus this, you get this. So that means that if you take this minus this, you get this. So the green vector is the difference, is the numerator. This. And I divide by h. When I divide by h, I just shrink it. Well, it depends. If h is very small, then actually I multiply by some large number. So this is done to rescale it, because if I don't do this, this difference is actually going to disappear. Because as the point goes closer and closer and closer, this is going to become smaller and smaller and smaller. And actually what I want to do is I want to take the limit of this. What I wrote was an approximation, and to make it more precise, I have to say it's the limit when h goes to 0 of this ratio. So if I didn't divide by h, I wouldn't get anything meaningful. I would definitely get 0 vector, because this green thing will shrink to 0 if h goes to 0, because this point's going to be the same, so this vector is going to be the same, r minus r is 0. So what I do is I rescale by h. So I adjust for the fact that actually I'm getting closer and closer. And when I do that, it doesn't necessarily go to 0 anymore, right? So in fact, it is going to stay finite, and as the point gets closer and closer and closer, I'm actually going to get something which will be tangent, which is what I do here in this picture. So that's the reason. That's the reason why it's a tangent vector. It's a tangent vector in the following sense. There are many tangent vectors, because if I have one, I can always multiply by something, by any number. I can multiply by 5, by 10, by a million. It's still going to be a tangent vector, because when I multiply a vector by something, I don't change its direction. I only change the magnitude. So if the direction is the same, if it was a tangent vector to begin with, it will remain a tangent vector when I multiply by something. So this is slightly inconvenient, because you might get one vector using particular parameterization of the curve, and someone else may use a different parameterization and then get a different vector. They're not going to be that different, because both will be tangent, so they will both have the same direction. But one of them could be like this, and one longer or shorter. So it oftentimes is a good idea to agree on normalization. And so no matter which result we get, we might say, okay, let's find a vector which has a unique length. So then what we need to do, and that's a vector which is called t0, is obtained by dividing this tangent vector, the raw tangent vector that we get by taking the derivative and dividing by its length, by its magnitude. Because when you divide a vector by its magnitude, you're going to get something of magnitude 0. Magnitude 1. I was jumping ahead of myself, because what I was going to say next is that this only makes sense if this is not 0. But of course, only assuming that t0 is not 0. It's possible that this vector is 0 to begin with, so then we can't normalize it, it is 0. But if it is not 0, we can divide by its magnitude and get a unit vector. So this is called a unit tangent vector. It's still not exactly unique, because there are two of them now. It could be this one, it could be this one, but the ambiguity is much less now. There are two possibilities. So it could be very useful sometimes. And at the end of last lecture, I used this derivative, this tangent vector, to write down parametric equation for the tangent line to this point. Parametric equations for the tangent line to this point, to the curve at this point. And these are very easy to write, because we know what the initial point is. It's just x0, y0, and z0. And all we need is the components of the tangent, of a tangent vector. And we have found a tangent vector by taking the derivatives. That's the top line on this board. So that's going to be f prime of t0. And now I have to choose an auxiliary parameter for the line. And it's better to choose a different parameter than for the curve, because we don't want to indicate that they kind of go hand in hand. They don't. The tangent line we're talking about is this tangent line on which this tangent vector lies. it only has something to do with this curve at this particular point. A priori, it has nothing to do with this curve at this point, or this point, or that point, right? So there's no reason to call the parameter for this line also t, because t was used as a parameter for the original curve. It's better to separate the two things. We have so many different letters that we can use, so why not use a different letter? And the first thing that comes to mind is letter S, just the next one in the alphabet, so that's why we use that. But you can use whatever you want. So as long as it's in the Latin alphabet, I guess. As long as we can recognize what it is and use the same, can recognize it's the same one. So then you get these equations. And I explained how this works in a particular example last time. Are there any questions about this? Yes? Large T is the unit tangent vector. It's a vector which is obtained by taking the derivative vector and divided by magnitude, provided that the vector is non-zero. To be absolutely precise, I should say. Does that make sense? Okay. Anything else? Yes? Not really, because I subtract the position. So the position is no connection to the derivative. You see? It's really this vector. But I think what you're saying is, so the question was about whether this vector has anything to do with the position vector. And this might be, the reason why you might think so is because I draw it starting from this point. See? But that's just a matter of convenience, because this vector, I would like to say that this vector is tangent to this curve at this point. So it's better to draw it here to indicate that. But it doesn't mean that somehow I have to add the position vector to this. This is a vector of itself, right? I'm choosing to take as the initial point for this vector the point P. Whereas I chose as the initial point for the position vector the origin. And so, as I explained before, there's no reason to choose this or that point. It depends on the context. We can choose any point. In other words, a given vector can be drawn starting from any point. I could draw this vector, r prime, starting from this point, which has nothing to do with this picture at all. But it doesn't negate the fact that this vector is the same as this vector, as long as they're parallel and have the same magnitude. You see what I mean? So just the fact I draw it from here doesn't mean that I have to add to it the position vector. That's the derivative vector. And, well, that's the way it's defined. Does this answer your question? Yes, tangent vector is a velocity vector. That's right. So tangent vector can also be interpreted as a velocity vector. Right. That's a good point. Okay, so let's move on. One more thing before we move on. We have discussed now in detail differentiation of vector value functions. And as I explained, differentiation of a vector value function like this simply means differentiating the first component, the second component, and the third component separately. You can also integrate vector value functions. And this is something which will be useful also for us a little bit later in this class. And again, to integrate a vector value function, you simply integrate the first component, the second component, and the third component. So it's very straightforward. By the way, in the homework assignment, which was posted before, for this particular section 13.2, there was a bug in the HTML file. And I prefer to say it's a bug, but actually I made a mistake. So, so I made a mistake, and I cut a couple problems from this line. So I put them back now. And so, but please use the updated version of the homework assignment. I haven't made any other changes, just in 13.2. In this particular section about derivatives of vector value functions. Don't worry. This is just a couple of exercises which are very simple. I just didn't want to get the idea that what's this terminal about? Look, there were only exercises about derivatives, about tangent vectors for plane curves, and I didn't want you to get the idea that you don't need to know about derivatives for three-dimensional things in three-dimensional space. So that's all. All right. So let's calm down. And let's move on. Derivatives. Okay, so the next topic we need to discuss is functions of 2 and 3 variables. By the way, one other thing I remember now. For plane curves, there's a connection to what we discussed. For plane curves, there's a connection to what we discussed at the beginning of this course. By plane curve, I mean a curve for which everything happens on the plane instead of in space. So let's say in R2, you would have also vector value functions like this, which would correspond to curves on the plane in the same way in which the three-component vector value functions correspond to curves in space. And then again, the same thing happens, which is that the tangent vector could be found by taking derivatives at a particular point, could be found by taking derivatives of these components. Now, in what sense is this related to what we discussed before? You see, what we discussed before was not so much the tangent vectors, because at that time we didn't talk about vectors. We discussed the slope. So we had a curve now on the plane, okay, and we talked about the slope, which is the tangent of the angle theta. And we found the slope, and this is again a point t equal t0. And we found the slope as y prime divided by x prime, which, or whatever, dy dt divided by dx dt, which was g prime of t0 divided by f prime of t0. And now everything, I just want to show you that everything is consistent, because now we actually give more detailed information, not just the slope, but actually the tangent vector itself. And what I'm saying is that in this vector has two components. One of them is, the horizontal one is f prime of t0, right? And the vertical one is g prime of t0. So in fact, the tangent vector is